What at a minimum, and in as much of a nutshell as you can manage, does special relativity assert?
Right. So to really understand this, we need to go back to a theory that was around before, actually two theories that were around before special relativity. So the first theory we need to say something about is what's called Galilean relativity. So this is something that is sort of inspired from some statements that Galileo made. It's not quite the same thing as what Galileo said, but in any case, it's a view that's now called Galilean relativity. Think about being in a car, and suppose you're not the one driving. You're maybe sitting in the back seat, and you throw a ball towards the front of the car. Now, if you're sitting inside the car and you throw that ball, um, for you, let's say the ball is going at 10 miles per hour. Um, I'm just picking a number at random, basically. It doesn't matter what number I say here, but let's suppose from your perspective, inside the car, it's going at 10 miles per hour forward. But suppose the car is also traveling, and relative to someone who's standing on the side of the road, they would measure your car as going at, say, 40 miles per hour. Well, if your car in 1 hour advances 40 miles, and um, and the ball is inside the car also going forwards, well then its speed is going to be increased by the speed of the car. And if you let the ball just continue going forward, in other words, if you don't like stop it at the front of the car, then in that same hour that the car goes 40 miles, the ball is going to travel, well, 40 plus 10, 50, 50 miles, right? Because it's got that extra oomph from the fact the car is already moving. So in order to figure out the speed of the ball, we need to add together the two speeds. We need one extra piece that Galileo would have thought about. And that extra piece is that whenever you determine how fast something is moving, we have to make use of two things. We have to make use of a clock, right? So we measured an hour in the example I just gave you. We have to make use of a ruler as well, right? So we measured that 40 miles or 50 miles. Imagine a really long ruler. We use that ruler to measure a distance. Now, since if you think about someone who's carrying that clock and that ruler along with them, how fast they're going to measure other people as traveling is going to depend upon how fast those other people are moving relative to them. So, for example, if you consider not the person that's on the side of the road watching you pass by, but someone who's keeping pace with you in another car, also traveling at 40 miles per hour, well then you don't advance along their ruler as the passenger in the car, right? On both of your rulers, you remain at the same place over the hour according to those rulers. So your speeds relative to each other are zero. And the ball speed relative to both of you, because it relative to both of you advances at 10 miles per hour, well, using a ruler and clock, either yours or in the other car, you're going to measure that speed as 40 miles per hour. All right, so in the Galilean picture, all speeds are relative because everyone carries around their own ruler and their own clock. Now, another theory that was around before special relativity was a theory that came about in the 1800s by a physicist named James Clerk Maxwell. And Maxwell has a set of equations that are going to describe electric and magnetic fields. So, if you take some iron filings and you sprinkle them around, say, a magnet, then you'll see the lines of force around the magnet. And there's also an electric field that surrounds us all the time. So if you rub a balloon on your head and your hair sticks out, that's your hair responding to an electric field. The idea in both these cases, with respect to the magnetic field and the electric field, is that all around us, all the time, are these invisible fields that anything that has either a magnet or a charge, an electric charge, is going to respond to by altering its motion. Maxwell's equations have one further consequence, and that's that light turns out to be a wave in the electromagnetic field. And in fact, it's not just light, but also like infrared radiation and ultraviolet light and radio waves. They're all different versions of the same thing with different frequencies. They're all different waves in this electromagnetic field. Well, it turns out that Maxwell's equations imply that the speed of light is a constant. And that's because using Maxwell's equations, you can calculate the speed that an electromagnetic wave needs to have. And it turns out that it's a speed that's determined by two constants. One constant that's known about through magnetic experiments on magnets, and the other constant that's known about through electrical experiments, so experiments involving like electric charges and so on. And because the speed of light is calculated from those two constants, it now means the speed of light is going to be the same for everyone, no matter which ruler or which clock you use. Well, that means that something has to give. Either Galileo is right and all speeds are relative, or Maxwell is right that there's a unique speed that's absolute, that's the same for everyone. In the period immediately after Maxwell, so in the late 1800s to the early 1900s, what people generally expected was that it was Maxwell's equations that had to change. It didn't seem reasonable to them that there could be a speed that's the same for everyone, that the speed of light, like every other speed, needs to be relative. So they thought about different ways to modify Maxwell's equations, different experiments you could do to demonstrate those modifications. What they eventually realized was that that was the wrong path, because no matter which experiment you cobbled together, you couldn't find a violation of Maxwell's equations. The genius that Einstein has is that the thing to modify is Galileo and not Maxwell. So on Einstein's picture, the speed of light is going to be measured to be the same value for everyone, even though all other speeds are going to be relative. And this is going to have a whole series of really counterintuitive consequences that people are still trying to grapple with today. So, to look at some of these counterintuitive consequences, let's first think about simultaneity. So, two events that happen at the same time are said to be simultaneous. Well, imagine that you have a train, and there's a car in the train, and in that car there's a person, and they're standing at the center of that train car. Now, from their perspective, according to their ruler and their clock, lightning strikes the front of the car and the front of the train car and the back of the train car at the same time. It's simultaneous, according to their clock. And because it strikes the front and the back, and the signal from both ends is traveling at the same speed, the signal from either end will reach them at once, right? So when they receive the signal from the front, it's the same time that they receive the signal from the back.
So just to make sure I'm comprehending there, we are assuming the frame of reference or perspective of someone on the train car, within the train
That's
car.
right.
And there are two bolts of lightning, one at the back, one at the front, and they're moving at constant velocity. And so,
Yes.
So from their perspective, they could think of themselves as being at rest, and everything else moving around them. And
Yes.
it's for that reason that if the lightning strikes at front and back, then they will calculate it as happening simultaneously.
Right. I mean, you've gone a step beyond where I was yet getting, but yes, that's right. So, from their perspective, the two signals arrive at them at once, and as far as they're concerned, that's because the two lightning strikes were simultaneous. We'll now consider the perspective of someone who is not on board the train, not moving with the train, but standing on, say, a platform next to the train tracks. And they're watching the train go by. Now, in order to figure out what they will see in their perspective, we have two constraints. One constraint is that if two things happen at one location according to one person's perspective, then according to anyone else, those two things will also occur at one point. So in other words, because the person on board the train car says that the two signals arrive at them at the same time, the person on board the platform must also say that those two signals arrive at the location of the person who's in the center of the train at once. So we're going to keep that fixed. And the other thing we have to keep fixed is the speed of light, right? Because we're wondering, how do things change if we adopt this perspective from Einstein that the speed of light is the same in all reference frames or from all perspectives. Well, with those two constraints, notice the following. The signal from the front of the train car has a shorter distance to travel to get to the center of the train car than the signal from the back. And that's because as the train car moves forward, it sort of helps, it means that the signal from the front has less distance to cross to get to that central location. And for the exact, basically same reason, because the train is moving away from that back location, the signal from the back is further to travel. Well, both of those signals travel at the speed of light. Then the one that comes from the back is going to take longer to travel than the signal from the front in order to reach that one position in the middle of the train car. Now, if the signal from the back is going to take longer than the signal from the front, what that must mean is that the lightning strike happens earlier than the lightning strike at the front. So part of keeping the speed of light the same in all reference frames, one of the consequences is going to be that what's simultaneous from one perspective or in one reference frame is not simultaneous in another reference frame. Now that's going to have another consequence, and that's that the length that objects have is also relative.
Now let me just step in real quick just to make sure that I'm understanding it. The reason that someone on board the train, within the train car, will calculate will receive the signals at the same time is that from their vantage point, the speed of light in either direction has to be the same. It's not like that when the direction into which they're moving, they would measure the speed of light as traveling faster than the speed behind them.
That's right.
Or
yeah,
that's right, because they're moving towards
the speed of light is the same from everyone's perspective.
The speed of light has to be the same from back and front. And the distance between where they are and where the signal happened is going to be the same. The whole thing is moving.
That's right.
And so therefore the time it takes has to be the same. So
that's right.
They will receive it at the same time. Okay. And then, however, that same constraint doesn't hold for someone who's watching the train car go by. They will be able to say, so you would hold the speed of light constant, but you are able to change distance because they're not on the train car. And so, is that right?
Yeah, so from the perspective of the person inside the train car, we can think of their perspective as being one in which the train is at rest, and the ground underneath the train is moving by, and then they're equidistant from either lightning strike, and the two lightning strikes, the signals from the two lightning strikes, as long as those signals travel at the speed of light, will reach them in the same amount of time.
Okay.
And then from the perspective of the person on the platform, the signal that, in their perspective, it's not the ground that's moving. The ground is at rest relative to them, and the train is moving. And then if they say that the speed of light is the same, that the two signals traveling at the speed of light have to intersect at one point, then the signal from the back, because it has further distance to travel, must have happened earlier than the signal from the front.
Right. Okay. Good.
So now so lengths are also relative, and here's a way that you can sort of immediately see this. The way to immediately see this is that is to think about what you mean when you say that you measure the length of something. So if you hold your ruler up to something and you measure its length, then what you're really talking about is the simultaneous position of its front and back, right? Because if you want one end of the ruler to line up with one side of the object and the other end of the ruler to line up with the other end of the object, you're measuring the simultaneous locations of the front and back.
Right.
But if simultaneity is relative, then in different perspectives, or in different reference frames, as it were, people are going to say different things about where what the simultaneous locations of the front and back happen to be, And so if something, for example, moves by you at very close to the speed of light, then according to your reference frame, it will be foreshortened along its direction of motion. And of course, the effect here is symmetrical, is reciprocal. So if you are watching someone go by in a rocket and you see their, well, how do I say this? You calculate that the rocket is scrunched up, then from their perspective on board the rocket, you will be scrunched up.
Okay, that was always my question is like, okay, this idea of length contraction, you're observing a rocket and it gets closer and closer to the speed of light. From your vantage point, it shrinks up more and more and more. And from your vantage point, it looks like processes are happening slower and slower. And where you approach this limit point where it stands still in time. Does the reverse also hold? Someone on the rocket, when they look out at the Earth trailing away, what do they see? Do they see everything scrunch up and go slower and slower and slower?
Yes. So
Okay.
the way that you put it makes me sort of, so there's a subtlety here that's not often brought up in these discussions. So when we say that that's how it looks, what we really mean is if you calculate where things are in the coordinates that you adopt for your reference frame, then that's what you would say. However, objects have more than just length; they have depth, and there's an additional effect here, what's sometimes called optical relativity. So here the question is, what you actually see with your eyes.
Yes.
And there you actually get a different answer.
Okay.
So if you watch a rocket ship travel by at close to the speed of light, then the rocket ship that you see travel by, according to what you see with your eye, is not foreshortened along its direction of motion. Rather, it's actually rotated. So you'll be able to see a side of the rocket that you wouldn't have normally been able to see given your perspective with respect to the rocket. And if it travels by a faster speed, the more rotated it will actually be. So that's an effect that's almost never brought up in these discussions because it's already difficult enough to get your mind around the idea that it's foreshortened.
Right.
Now
I'm like, I've seen a ton of diagrams where the ship gets smaller and smaller and smaller.
Yeah, that's right. So it's what you see with your what the foreshortening is what happens mathematically. But that's not the same thing as what happens if you like trace out all the rays of light that come off of the rocket
Okay.
and you trace those back to someone's eye.
So is there a
They
sense
will
in
actually
which
be subject to an optical illusion.
Yeah, that's what
The
I was going to
optical
say. There's a
illusion is
sense
also
in which
rotated.
like the length really does contract. It's just that because of the way light works in this given this phenomenon, it will look like it's rotating.
That's right. Yeah. Yeah. So the rotation is an optical illusion, and the foreshortening is what physically happens according to your reference frame. And
Good.
their reference frame will see the exact opposite. From their perspective, they're not foreshortening at all. They're staying the same because according to them, they're at rest. One way to think about this is that according to everyone's own ruler, since they don't advance along their own ruler, they're at rest relative to themselves. But since the other person moves along their ruler, they'll see that person as, they will calculate that person was foreshortened, and they will see that person as being rotated.
Okay. Is there that tangential point, but is there any similar optical illusion concerning what they would see if they could perceive clocks on board the rocket? Like, I imagine if you could see this, you would see things slow down, right? Time dilation would happen. Is that
You get time
is that one
dilation,
right?
but that's right. But you also there is an optical effect, and that's that it has to do with the frequency of light that you are receiving from them. So, this is what people call the Doppler shift that happens
Yes.
with waves. There's a relativistic version of the Doppler effect, but for people, for audience sake, when you hear an ambulance passing by, you hear the pitch of the siren change. The same thing happens when an object travels by you. So as you approach an object, it gets blue shifted, and as you move away from an object, then it's red shifted. And the reason why that is, if you think about this. Suppose that something is moving and it's depositing objects as it travels along. If it's moving away from you, then the distance between the objects that it's like laying down is longer and longer. And if you approach it, then the distance between those objects is foreshortened.
Right.
And the consequence of that is that you'll see a shift in its frequency. The bluer is higher frequency, the redder is lower frequency. So if something is moving away, the frequency is downshifted, and if it's heading towards you, the frequency is upshifted, so it's shifted towards the blue.
Okay. So that, would you say, everything you've said here, that is a nutshell explanation of special relativity?
Yeah, hang on.
Or are there any other components?
There's like this stupid thing I'm trying to close out that's not. Well, anyway, there's like thing come from my screen that I couldn't close. There is one more component, and that's what's called time dilation. So not only is time symmetric in that not only is time relative in that the simultaneity is relative, but so too the time interval between two events is relative. Here's how that works. Suppose we build a very simple clock, and the way the clock works is that it's got two mirrored surfaces, and light travels from the bottom, bounces off the top, and comes back to the bottom. And it keeps going like that, and each time it makes a round trip, we call that one tick of our clock, and by counting up the number of ticks of our clock, that allows us to keep time. Well, suppose that our light clock is moving in the direction that's parallel to the two mirrored surfaces. If it's moving in that direction, then by the time it gets back to the bottom will have shifted over some amount, right? So to go on a round trip journey, it takes more time for the light to get back. And so the consequence here is that clocks slow down if you see a clock on board, say a rocket moving past you close to the speed of light.
Okay, yes. And so it's not just that simultaneity is relative to reference frame, but moving clocks run slowly. So intervals of time, how would you phrase this? Intervals of time change in their duration?
Yeah, that's right. I mean, we have to be careful because sometimes the way that this is put isn't quite technically accurate. So people will say things like, "Oh, how time passes changes." But that's not the right thing to say, right? Because the passage of time is, at least in philosophy of time, is a sort of quasi-technical notion that we get from something like the A theory of time, where people talk about objective passage. And here we're not talking about that. We're talking about the amount of time that, according to a clock, passes, or the duration of time as measured by a clock in terms of the number of ticks that it goes through.
Okay, that is good. Now, in my younger, more precocious days, I read some of William Lane Craig's work in the philosophy of time, where he attempts to integrate the special theory of relativity with what we might call the A theory of time. And we'll get to what all that is. But in the process of that, he distinguishes three interpretations of special relativity. So on the one hand, he has what he calls the Einsteinian interpretation, the Minkowskian interpretation, and the neo-Lorentzian interpretation. Now, I think all of them would agree with the minimal points you've made, that in special relativity, you have rulers scrunching up as they move, and you have clocks going more slowly as they are in motion, approaching the speed of light. But the point of departure with some of these will be what they think that means about space itself and time itself. So they might want to make a distinction between, time itself and our measurements of time. But in any case, what are these three interpretations? Do you agree with that three-tiered classification, even if you think, one of them is obviously wrong? And then what do they assert?
So the first thing to be said here is that this, there's two things that should be set up front. One of them is that the idea that these are different interpretations is not the way that people in, say, philosophy of physics would think about the issue. So it's now thought that thinking about different, say, interpretations of, say, quantum mechanics isn't technically accurate. That in the case of interpreting quantum mechanics, what they are they're not really interpretations. They're distinct theories.
Right.
They're distinct theories that may have many of the same empirical implications, but they make distinct claims about the world and are for that reason distinct theories. Likewise, when it comes to relativity, we should say these aren't truly different interpretations, but rather they're different theories that make many of the same empirical predictions that ultimately say different things about the world. That if one were true, the others wouldn't be. The other thing that should be set up front is that the three-tiered classification here is sort of Craig's way of dividing things up. I haven't really seen people in, say, philosophy of physics divide up things that way. There is a very live debate in philosophy of physics about different ways of understanding relativity, but that's between what's called a geometrical interpretation and a dynamical interpretation. Those two views don't sort of fit into Craig's classification system. I mean, they kind of all would fit into what he calls the Minkowskian interpretation. But anyway, setting aside those two caveats, we can ask, okay, what does Craig mean by each of these three? So the Einsteinian view here comes out of the way that Craig interprets Einstein's 1905 paper on the electrodynamics of moving bodies. In Einstein's studies, there's a debate about what exactly Einstein's view was, but what Craig calls the Einsteinian view is how Craig interprets Einstein's 1905 paper. In this view, it's true that you have all of these effects about what happens to clocks and rulers and all the other effects I've already told you about. But we shouldn't understand those effects in terms of a four-dimensional space-time. Instead, what we should say is that there's some way in which every observer occupies their own reality. So there's all of these different, almost disconnected realities that are experienced by different observers. Today, this is a view that's sometimes called a fragmentalist view about relativity. And one of the pieces of evidence that someone could give that's the right way to understand Einstein's 1905 paper is that when Minkowski comes around a few years later and gives a four-dimensionalist interpretation, Einstein's initial reaction is to say that he doesn't understand what Minkowski is doing. So whatever Einstein thought he was doing in 1905, it wasn't obvious to Einstein that he had been doing the same thing as Minkowski's doing. However, the other thing to keep in mind is that eventually, and well before 1915, when Einstein publishes his work on general relativity, Einstein comes to accept Minkowski's view, and that's important for where general relativity comes from.
Right.
All right. Well, what is this Minkowski perspective? So, Minkowski's view was that it's not that there's all these different fragments or these different realities. There's one reality. It's an absolute reality. But it's not a reality of lengths and times. It's a four-dimensional reality that we call space-time. Here's an analogy that's sometimes used to explain what's going on there. So imagine you had a bunch of people that are standing around a barn. And since they're looking at the barn from different points of view, and what they see in their visual field is like a projection of that three-dimensional barn onto their two-dimensional field of view. And in that projection, they'll have different perspectives of what the barn looks like, right? Like one person might be at the front of the barn, and on their projection, the barn is a particular shape. Someone else who's a different part of the barn will see a different shape. They're all looking at the same one barn. That's maybe one thing of an absolute reality, but they have all different perspectives on that one absolute reality. So Minkowski's view is that there's this four-dimensional absolute reality that underlies all of these lengths and durations of time and simultaneity. That all of those things are relative. And one of the pieces of evidence one might give that Minkowski was on the right track is that if you calculate not our ordinary three-dimensional lengths that we're used to, but a kind of four-dimensional length within that space-time structure, then you find out that that four-dimensional length is not relative but absolute. Moreover, another reason you might give for thinking that Minkowski was right is that the mathematical tool that we use to go from one reference frame or one perspective to another, like from the inside of the train to the person on the platform, what's called a Lorentz transformation. It turns out that those Lorentz transformations are actually equivalent to a kind of rotation in this four-dimensional space. So in space-time, if you think about rotations in space-time, those rotations are equivalent to Lorentz transformations. All right.
So it's kind of, let me see if I can connect a few dots here. I like this idea of like the barn, and then, depending on where you're at, it will look different, but there is one absolute reality that's kind of like the conglomeration of all of them. So if I understand correctly, relative motion reorients someone in space-time. So it almost like rotates you so that you are getting now a different slice of space-time. You're not changing
It's
anything.
literally that's right. It's literally a rotation. And so like if you look at what happens in space-time, it literally is a rotation. But there's a caveat that's important here, and that's one of the ways that space-time differs from our ordinary three-dimensional space. So people think back to maybe their high school math class. If they ever had to calculate the distance between 2 points from their coordinates, there was a formula for doing that.
Yes.
The formula turns out to be just the Pythagorean theorem.
Right.
And the reason why the Pythagorean theorem gives us distances is because if you think about your right triangle, then the distance along the hypotenuse of the right triangle, that's what the Pythagorean theorem gives you. And so you can think about the distance in three-dimensional space in terms of that object, where you add together the squares of a bunch of things, right? So you add together, for example, the square of the length along the base and the square of the length along the height of your right triangle. Now, in four-dimensional space-time, you're not just adding squares of things. So one of them, the time piece, right? So we still have a formula that has the squares of a bunch of things. However, when you put the square of time in there, you put that piece in, instead of getting a positive sign next to it, it gets a negative sign. Now that fact, where we have a version of the Pythagorean theorem where one of the terms gets subtracted instead of added, that means that the kind of geometry that we're talking about is what's called hyperbolic geometry. And in hyperbolic geometry, the rotations look a bit different. But if you do a rotation in a hyperbolic space, then that's equivalent to a Lorentz transformation. So those are the kinds of rotations that we're talking about.
Good. Okay. So that gives us the Einsteinian interpretation, which I think if we grant that Einstein really did have it, or even if he didn't, there still is this theory that we don't unify space and time into space-time. We allow for three-dimensional objects evolving through time. It's just that if you do that, it leads to this kind of weird picture where a person in their reference frame seems to inhabit their own space and time. And it's this huge fragmentation of reality. Whereas what Minkowski allows us to do is unify the whole thing into one four-dimensional structure, space-time. Okay. So then you have the neo-Lorentzian theory, which I'll drop interpretation. We'll just say theory. You have that theory whose chief selling point is that it can allow us to maintain our more intuitive separation between space and time. It can allow us to hang on to absolute simultaneity. It can do all of these things and still affirm the mathematics of special relativity. How does it do that?
So one thing to be very careful about is that it doesn't preserve all of the mathematics of relativity.
Okay.
So this is a piece that often gets glossed over, that even Craig doesn't talk about very often, despite being one of the main proponents of this theory. But what it does give you are the Lorentz transformations, and the idea here is that the foreshortening of objects along their direction of motion, the change in the duration of time as measured by a clock, all of these kinds of relativistic effects that come out of the Lorentz transformations, those effects, according to the neo-Lorentzian, are actually illusory. What's actually going on is that there are forces or influences that somehow alter all of our measuring devices. And they alter all of our measuring devices in such a way that it gives the appearance of special relativity. It gives the appearance of the Einsteinian or Minkowski picture. So this comes from, historically speaking, in some sense, this was a view that was thought about before Einstein. So, it comes from this guy, Lorentz. I mean, this is neo-Lorentzian we're talking about. But Lorentz himself had a similar view. Lorentz noticed a few different kinds of observations. So they've been doing experiments to try to measure the speed of light in different directions as the Earth travels around the sun, for example. And what they expected was that the speed of light wasn't going to be a constant. And we're back to our conflict between Galileo and Maxwell. People thought you had to modify Maxwell. And so they're looking for violations of Maxwell by measuring the speed of light in different ways. Well, because they failed to find any situation in which the speed of light were different, Lorentz comes up with this idea that maybe what's going on is that all of their measuring devices are being systematically affected to cancel out the change to the speed of light. And if that's right, then it gives you a very similar mathematical structure as what Einstein has in his 1905 paper. It gives you the Lorentz transformations, for example. I mean, this is why they're called Lorentz transformations, because Lorentz discovered them before Einstein did. But Lorentz is a very different picture of where those transformations come from. On Lorentz's view, they come about because there's these systematic effects, forces or influences or whatever, that somehow affect all of our measuring devices. So we never really succeed in measuring the speed of light. We never really succeed in measuring distances or times. What we actually measure are these other things that are sort of affected by these influences that are on all of our measuring devices. There's an analogy that Henri Poincaré came up with that sort of helps to explain what's going on in this view. So Poincaré imagines a universe that consists of a bunch of creatures who are sort of floating around, or maybe they're swimming around inside of a big sphere. And according to the laws of their world, as they get closer to the edge of the sphere, every possible way of measuring distance shrinks. And if they get all the way to the edge of that sphere, then every possible way of measuring distance will shrink to zero size. Now, from the perspective of the creatures living inside of that sphere, what they will think is that the sphere that they live in is actually infinitely large, right? If they're their rulers shrink up in that way. So we can. So what Poincaré says is that any determination of the geometry of your world is going to make it an assumption about the forces that act on your measuring devices. So what neo-Lorentzians say is that, well, there's these forces that universally act on all of our measuring devices, on any possible measurement of time or space that you could make, that gives this appearance of relativity, even though in actuality, time as it actually is, doesn't depend upon your reference term. The time, they would say, is actually absolute, as is space.
Now, when you describe it like that, it has an air of implausibility to it. Because it seems mysterious that there would be this universal, exceptionless work that systematically deceives us, like the inhabitants of a finite bubble that appears infinite. So,
Yeah.
what do neo-Lorentzians propose as the physical force or mechanism by which clocks are slowed and rulers are contracted? Do they fill in the details?
So this is a big problem because they don't.
Okay.
So there's been different proposals that have been around. Craig, in his in the technical book that he has that goes through this stuff, Craig cites an author, a physicist named Prokofnik. So Craig is enamored with Prokofnik, but if you go in physics circles, basically no one knows who Prokofnik was. But Prokofnik was this guy that was around in the 1970s and 1980s that was a fan of Lorentz, and he has this view that maybe it's somehow the gravitational field that's going to do this work. But part of the problem here is that whereas Lorentz had a very definite physical picture of how all of this is supposed to happen, the picture that Lorentz had is no longer plausible. So in Lorentz's picture, it's going to be an influence from the electromagnetic field. So Helmholtz had noticed that if you take a spherical distribution of electric charge, if you somehow imagine that you get a ball of electric charge that doesn't like explode apart, right? If you bring together a bunch of negative charge, it's going to want to break apart. But ignore that, and just suppose that you could bring together a ball of electric charge. Then in order to remain in equilibrium with the surrounding electric field, when that spherical distribution is in motion, it's going to foreshorten along its direction of motion. And the way in which it's going to foreshorten along its direction of motion is going to be precisely the way that the length contraction, the Lorentz transformation for length, what that predicts. Now, that was because the reason why that was attractive maybe in the year 1900 was because people had these very speculative ideas about how atoms or molecules were going to work. They knew about electromagnetic forces, but none of the other three. They knew about gravity and they knew about electromagnetism, but they didn't have our theory of gravity, and they didn't have a clearer conception of any other force other than electromagnetism, because the physics of the forces didn't exist yet. And so from their perspective, they could imagine that, well, if the consequence of the electromagnetic field is to bring about things that look like these Lorentz transformations, then we can imagine that maybe what happens to atoms and molecules in general brings about these kinds of effects. And then all the atoms and molecules in our measuring devices have these effects brought about for them, and then that would cancel out the fact that we should be seeing a different speed of light. Now, people today have a very different conception of fundamental forces, as I was saying, and at least among the fundamental forces that are standardly recognized by physicists, none of them are going to have the effect of systematically bringing about those Lorentz transformations. So you have to posit that there's some other influence wholly unprecedented in physics as we currently understand it, is going to bring about this effect. So it really, from in that way, ends up looking like this like really skeptical hypothesis, right? That we're sort of systematically tricked by nature into believing in something that is not the way that nature really is. However, Craig would turn around and say that the standard Minkowski picture actually deceives us in a much worse way. So, Craig would say that it's completely undeniable that time passes.
Right.
Right? It's this really fundamental aspect of our experience, he would say. So fundamental, so important, so obvious, so immediate to us, that any theory that denies passage rules itself out. And on the Minkowski picture, it looks like time doesn't objectively pass, because all parts of the space-time block, all parts of that four-dimensional space-time reality equally exist. And so if that's right, it's not going to be that, for example, as Craig thinks is true, that the future events come into existence as they become present and go out of existence as they go into the past. So Craig would say, okay, sure, there is a way in which neo-Lorentzianism is a kind of skeptical hypothesis, but the Minkowski picture is a much worse skeptical hypothesis. And now it's, the part of what we need to worry about here is like which one of these pictures is a worse trade-off than the other.
Yes.
At least when it comes to thinking about them as skeptical hypotheses.
That's a good point. It does seem on its face anyway that skeptical worry, that's going to cut both ways between neo-Lorentzianism and the Minkowski view. I think a worse issue, though, is that there is no force recognized by physics today that would account for length contraction and time dilation. That's a real problem. What is the view among physicists and perhaps philosophers of physics today about neo-Lorentzianism? Is it pretty much universally rejected? That's my vibe.
Yeah, I mean, many people don't even know that it exists.
Right.
And the people that do would be very skeptical about it. There are people who think that. Sorry, I gotta plug my laptop in. There are people who think that there are important lessons that we can learn from Lorentz. That the discussions people had around the time that special relativity was born are still going to be important for how we end up interpreting relativity. But this idea that we're going to have a return to absolute space and absolute time because the world somehow systematically tricks us, that's not something that that people think is very plausible. There is a view that sometimes introduced when people are talking about how we ought to interpret quantum mechanics, that maybe there is a reason to return to something like absolute time or absolute simultaneity, because there's some people who think that things like entanglement in quantum mechanics require some kind of absolute simultaneity. So this is like the view that Tim Maudlin has,
right?
For example.
I was just going to say that.
But he would couch that in a very different way than Craig would. And like we've said, I think it's quite important that there isn't this mysterious force. Like, that's not something that's widely recognized.
Yes.
So, right, I think that's a fairly deep problem for the neo-Lorentzian, and in fact, it's going to be worse when we try to talk about cosmology. Now, one of the things that happens in philosophy of religion is that because Craig is such a big presence in philosophy of religion, unlike philosophers of physics, many philosophers of religion do know about neo-Lorentzianism and see it as one of the options on the table.
Okay.
So if you look at, like, for example, Ryan Mullins' books, I think Mullins has a lot of really great stuff to say about philosophy of time and about theology, and I think he's a really smart philosopher of religion. But if you look at what he's written about philosophy of physics, uh, I find it it gets under my skin in a way, that is like irritating to me. So he thinks that because he's so strongly committed to A theory, and Craig is such a big presence in philosophy of religion, that we really should be neo-Lorentzians. And then the other thing that sometimes happens in philosophy of religion is this idea that somehow, when it comes to general relativity, that's going to be a more hospitable home for neo-Lorentzianism than special relativity. And people think that because there are some general relativistic models, some ways of thinking about the way that space-time could be, that people have argued involves a return of absolute time. And so the thought here is that, well, maybe general relativity, for precisely that reason, gives us a better home for the neo-Lorentzian. However, I don't think that that's really the right way to understand general relativity. And part of that is because of the way that general relativity includes special relativity. So we can ask, what does it mean when we say that space-time is curved? And it's a very funny sort of thing to say, because people might imagine that it would mean that space-time is curved into a higher dimension, that maybe four-dimensional space-time is curved into, say, a fifth dimension. But that's not right. That's not what physicists mean when they talk about the curvature of space-time. There are two different ways to talk about the curvature of a surface. There's what's called extrinsic curvature. So extrinsic curvature is about the way that one surface might be curved into a larger embedding space. So for instance, if I take a piece of paper and roll it into a cylinder, then I've curved a flat piece of paper into a higher dimensional space. I've given it some extrinsic curvature. However, that kind of curvature is usually undetectable. Right? If you're on that flat piece of paper, and what you can see is a small enough region of that flat piece of paper, then you don't know that it's been rolled up into a cylinder. The kind of curvature that you can detect if you're living in that surface is what's called intrinsic curvature. So suppose that you take, say, a rubber sheet, and you press your hand down into it so that the sheet gets bent by your hand. Because of the way the sheet is distorted by your hand, it now has intrinsic curvature. In general relativity, what happens is that space-time is intrinsically curved by the presence of matter, energy, or momentum. And the way that that intrinsic curvature happens results in a change of the motion that objects go when they're subject to no forces at all. Right? So in Newtonian physics, what we call inertial motion, when something's moving inertially, there's no forces acting upon it. And in Newton's view, that's when an object is moving like that, it moves at a constant speed in a straight line. Something very similar is true in general relativity. So if you think about a curved surface, like say a globe, if you go very, very close to a point on the globe, say that you're making a map of the city of Chicago, your map of Chicago is basically just flat. To map Chicago, you don't need to worry about the fact that the Earth is curved. Well, the way that we can think about that geometrically is you can think about a bunch of flat pieces of paper that touch the globe at one point, so that for every point on the globe, there's a corresponding flat map, a flat piece of paper that for every point on the surface of the Earth touches the Earth at just that point. And then by thinking about what happens as you go from one flat map to another, the relationship between each one of those flat maps tells you the intrinsic curvature of the Earth's surface. And so the part of what that means is that what we might call the standard of straightness, what looks like a straight line, changes from one point to another. And the way that change happens, that's what mathematicians call a connection. And then that connection gives us it tells us information about how the surface is curved. Now, if we extend this to four-dimensional space-time, then instead of having flat pieces of paper at each point on the Earth's surface, we have an entire three-dimensional, really four-dimensional space. And that four-dimensional space that we think of as being at each point, what's called a tangent space, is just a copy of the space-time we had in special relativity. So just as you have a bunch of different flat descriptions that we glue together into a curved description when we think about mapping different parts of the Earth, so too when we think about curved space-time, we glue together a whole bunch of locally flat descriptions to think about how space-time as a whole is curved. Now, if we think about moving from special relativity to general relativity, well, what are we going to say for neo-Lorentzians? I mean, would we say that we have that absolute space and time, but a different absolute space and time for every point in the four-dimensional space-time? It seems like they don't want to say that. Moreover, part of what they wanted to say with respect to special relativity is that their neo-Lorentzian view picks out a special absolute reference frame. Well, in general relativity, unlike special relativity, there is no reference frame for all of space-time. Your reference frame lives inside your local tangent space. So as you go from one point of space-time to another in general relativity, no matter what path you take to get from that one point to that other point, you're now moving from one reference frame to another. In fact, this is part of how Einstein discovered general relativity in the first place. Because part of what Einstein could think about is what happens when you change a reference frame in special relativity. So for instance, suppose I've got a big disk, a big wheel. And what I do is I have rulers along the circumference of that wheel. If the wheel is moving at some very high speed, then each of those rulers will be contracted, right, because of length contraction. However, the diameter, because it's everywhere perpendicular to the direction of motion of those little rulers, doesn't change. Well, pi, the mathematical constant pi, is the ratio of the circumference to the diameter. So because the circumference changes but the diameter doesn't, that means that you'll no longer calculate pi as having the same value. Now, because the points along the circumference change their direction of motion as they go along that circumference, they're changing from one reference frame to another. So what this kind of gives you is some intuition that it's kind of heuristic argument. It's not a very rigorous argument, not very precise, but it gives you some reason to think that maybe there's something about going from one reference frame to another that involves some kind of non-Euclidean geometry. In special relativity, that non-Euclidean geometry is only apparent. But the insight in general relativity is that there's no reference frame that you can go into that will get rid of the appearance of curvature. And so that's just like on the Earth's surface. There is no flat map that you can have locally that will give you, that when extended out, gives you all of the Earth's surface without distortion. Right? Likewise, when you go from one location in space-time to another, you have no choice but to change your reference frame. Precisely because of the curvature of space-time. So if you did pick out a special reference frame for each point in space-time, then in the general relativistic context, you won't be picking out a preferred reference frame for all of space-time. So if you follow through what the neo-Lorentzian wants to do, you don't get the consequence that they wanted.
So if one is a presentist, such as myself, who wants to maintain that there is an objective distinction between past, present, and future, and the only things that exist are present things, if future
Yeah.
things do not yet exist, past things no longer exist, what is one to do with
So
special relativity or general relativity, but even just focusing on special relativity? What is one to say if not go the neo-Lorentzian tact?
it's not clear to me what it is that someone should say. I mean, part of the problem here is that, uh, so we've got this formal or mathematical structure handed to us by the theory, right? This mathematical structure that describes what we typically call four-dimensional spacetime. And then the job is to find parts of that structure that we can identify as, say, the present. And now it turns out that no matter which structure we're going to try to identify as the present, none of them seem all that plausible. So, for instance, you could go the route that I was just talking about, where you talk about a preferred reference frame. In special relativity, the problem is that that preferred reference frame is completely undetectable. In general relativity, the problem is worse because, well, each point in spacetime has its own reference frame. There's no global reference frame. So there's no global present in general relativity, even if you could pick one out in special relativity. You could try some other things. So you could say that maybe, so if you're looking at like a particular point in space-time, there's all the signals that can reach that one point from its past light cone, and all the places the signals could be emitted from. So all the signals that that point can reach by emitting a signal, that's its future light cone. And then there's all the spaces that are neither the future light cone or the past light cone. It's called the absolute elsewhere. One proposal you could have is that the present is just that one point. And that looks like solipsism, so we don't want, that's not very attractive. Maybe the present is the bow tie shaped region, the absolute elsewhere. All the points that are not in your that are not in your future or past light cone. Well, now, first of all, everyone has their own separate present. But on top of that, someone could live out their entire life in your absolute elsewhere. So somehow their birth, growing up, middle age, dying, all the things that go through their entire life on this proposal would be part of your present. Would be part of what is for you, one moment of time. Well, that doesn't look very attractive either. Maybe the surface of your past light cone, maybe that's what you could pick out as the present. Well, that doesn't look very attractive because not only would that be different for each observer, but also it would mean that the path that light takes, so between light being emitted and light being arriving somewhere, all of that takes place in one moment of time or one instant of time. All of that takes place in what you would call the present. Well, that's not very attractive. So there really is this problem that, it looks like whatever move the presentist is going to make here, they're going to have to bite the bullet in some way. Though, of course, I mean, a committed presentist would tell us that the four-dimensionalist has to bite maybe an unreasonable bullet because they have to say that this immediate part of our experience, the experience of passage, that's somehow illusory. And so, we again come back to this problem of, like, which poison are you willing to swallow? When it comes to general relativity, the reason why it's sometimes thought to be a more hospitable home, and that's what we were talking about before, is that there's a way, in some general relativistic spacetimes, there's not just one spacetime model that general relativity gives us, there's an infinite number of them, but in some of them, such as the one that is standardly used to describe the Big Bang, what's called the Friedel-Lemaitre-Robertson-Walker spacetime, FLRW spacetimes. That's a family of spacetimes that can be sort of nicely chopped up into into hypersurfaces, into three-dimensional spaces, where each one of those three-dimensional spaces looks something like a moment of time. So then you might think that if you restrict general relativity only to those kinds of solutions, then you could recover something like the present. Because you could maybe pick out one of those hypersurfaces, one of those what's called a Cauchy surface, and call that the present. Well, part of what this is doing is it's restricting the solution space of general relativity, and there's no reason within general relativity itself to tell you to make that kind of restriction. And worse, if you think about what the universe is really like, it's not actually like those FL or W models. I mean, those are idealizations that you can get if you sort of average over all of the local unevenness in the universe. Right? So when we talk about cosmology, we're imagining that we're thinking about a scale where we've zoomed out so far that we're no longer able to distinguish between individual galaxies. The collection of all the different galaxies from this perspective is going to look like some uniform medium, like a gas that uniformly fills the universe. In that perspective, the universe is both isotropic, which means that it's the same no matter which direction you look, and homogeneous, which means that it's the same from one location to another, at least with respect to these hypersurfaces that we've picked out. But if you look at the way the universe actually is, well, when you go from points that are outside of the Earth to inside of the Earth, there's this abrupt change in density, right? Because outside of the Earth, well, in the atmosphere, you just have this gas, and when you go to outer space, you basically have more or less just have vacuum. But inside of the Earth, the density there is appreciably higher because it's rock, right? So if you look at the universe more closely, it's neither homogeneous nor isotropic, which means that it's not an FL or W spacetime, which means that it's not going to be chopped up in precisely the way that FL or W spacetime was giving you. Maybe you could still chop it up somehow. But notice that if the time parameter that you really cared about was that one that you get from that averaged out perspective, what Craig calls the cosmic time, the time variable that we often use in cosmology. Well, that's a time variable where the relationship between your own experience and that cosmic time is really rather unclear. I mean, in some sense, Craig even admits this because Craig makes a big deal out of the fact that we can detect the Earth's motion relative to the cosmic microwave background. So relative to the cosmic microwave background, there's one part of the sky that's hotter than another, which means that we can, in some way, like almost like we can detect our own motion relative to the universe, right? So Craig takes it that this is some suggestion that there's some absolute space and time. But if that's the right way to think about things, then why is it that our immediate phenomenal experience of the passage of time, the thing that we wanted to rescue in the first place, why does that have any relationship to this time parameter that we think about on these very large scales that don't match up with the motion we have here on the Earth? I mean, if it's true that the Earth is moving relative to the rest of the universe, then our clocks on Earth don't keep cosmic time, and the way that your mental experience keeps track of time is not cosmic time, right? It's this other time variable that is distorted by those universal forces, like the neo-Lorentzian is going to claim.
Well, I do not have a defense of Craig and neo-Lorentzianism, but I am one of those well, I wasn't at the time, but because I was 15. But I'm one of those philosophers who was taken in with Craig's articulation of special relativity and his defense of the A theory. I want to hang on to a presentist ontology in the A theory of time, but I now think that the neo-Lorentzian way of doing that is not very plausible, and that leaves me feeling defenseless against relativity. So there's more work to be done. I do want to go into the philosophy of physics. I'm making efforts to do so. So part of that will be exploring these things. And that might mean giving up the A theory, but I don't want to. So for whatever that's worth. But I appreciate you taking the time to articulate these things. I think you gave a really careful and helpful and understandable overview of special relativity. So thank you for doing that.
I think there's one more place we should go before we end this, and that place is that we should talk about the beginning of the universe, because I think that's what we're ultimately trying to get to, was like how would a neo-Lorentzian view affect how we think about, say, the Big Bang? And here, something that's really important is that we need a substantive physical theory in order to make an inference about the beginning of the universe, at least using any of our standard scientific ways of thinking. So, Craig and other defenders of the Kalam argument have a priori, purely philosophical arguments for a beginning, like the successive addition argument or Fermi arguments or whatever. But for just thinking about the scientific case, then we need a substantive physical theory. And the reason why we need a theory like that is because the beginning of the universe is not something that can be directly observed. Right? So we need to make a move that scientific realists standardly make, where, because we're committed to a realistic construal of some physical theory, we can infer something that isn't itself observable. Right? So maybe to take another context, maybe we're committed to there being such a thing as the electromagnetic field, even though we can't see the electromagnetic field directly. And we're committed to that because we're realists, maybe, with respect to, say, Maxwell's electrodynamics. Likewise, if we're realists with respect to, say, general relativity, and when we look at the distribution of matter energy in the universe and try to trace that distribution backwards through time, maybe we come up against a boundary that the universe can't be traced beyond, so where the universe, according to the model, must have begun. And then if we're realists, even though that's not directly observable, we would then have to endorse that apparent beginning. Well, of course, the neo-Lorentzian wants to say that we don't actually have access to space-time structure, right? Just like Poincaré's creatures, the rulers and clocks that we have are systematically distorted. So, just as Poincaré's creatures might think that their world is infinitely large when it's actually finitely large, so too we might mistakenly think that the past is finite when it's actually infinite. So part of the challenge here is for Craig to tell us enough about how a neo-Lorentzian theory would work, so that we know how to tell the duration of the past. One way you might think about this is that, well, there's different time variables that appear in physics. If you have this collection of hypersurfaces that look like something like instants of time, you might think of those time variables as labeling those hypersurfaces, right? And then, in virtue of one of those parameters that labels that series of hypersurfaces, maybe you could see that the past duration of the universe is finite. Now, Craig picks out a very particular one of those parameters, what's called the cosmic time. And indeed, there are at least some models where the cosmic time is finite to the past, right? And that's part of how the case is going to make for the universe having had a beginning. But why pick out the cosmic time? As I said, the cosmic time isn't connected with our phenomenal experience. And not only is it not connected with our phenomenal experience, but depending upon what kind of inhomogeneities the space-time has beyond the regions that are further than the furthest way that we can see, which is outside of the observable universe, for example, it may be that the cosmic time cannot be extended to those further locations. So, for example, suppose that something like an inflationary multiverse obtained? Well, within each pocket universe, you could have a cosmic time, but there wouldn't be such a thing as a cosmic time that you could use for all of the multiverse. You would need some other time variable. Well, people have come up with other time variables that you could use here. So, for example, there's something called the York time. People have argued that the York time has various different theoretical advantages, and maybe this is a better parameter to use. The one thing that's really nice about it is that the class of spacetimes for which you can define the York time is broader than the class of spacetimes for which you can define the cosmic time. Now you can ask about that series of three-dimensional hypersurfaces that the cosmic time will say go back only some finite distance. Is that what the York time says about that same collection of hypersurfaces? And the answer is no. As you go backwards through time, you find that the York time can go infinitely far back. And so on the York time, the universe is infinitely old, even though on the cosmic time it's finitely old. So then here's a challenge for Craig. Why pick the cosmic time as opposed to the York time as your measure of the past history of the universe? Or indeed, why pick any of the other physical measures of time that we have, given that he's going to have a view where absolute time is so thoroughly disconnected from the kind of things we can measure with clocks.
Yeah, I mean, that point always occurred to me when I was thinking about Craig's philosophy of time and a neo-Lorentzian interpretation, that it kind of advocates for a non-realist approach to general relativity and to the space-time distortion as the what gravity is. And I thought, well, surely that's going to call into question the applicability of Big Bang cosmology, which seems to rely upon general relativity. So,
Right.
I'm curious to see what Craig would say. I mean, I think he apparently is going to address some of these criticisms, or at least some of your work, replying to the Kalam, in his
Right.
third volume of his systematic philosophical theology. So, I'm curious and eager to see what he says, because I don't see
Yeah.
the way
So
out.
am I. I mean,
Yeah.
I think there's one other thing to notice here, which is that, so one thing that's really important that many people don't, for whatever reason, think about is that it's not enough just to say that we know that the universe was once hot and dense. I mean, the picture that I've met many people who, for whatever reason, they think that you can somehow go from the idea that the universe is hot and dense directly to a beginning. But the universe being hot and dense really has nothing to do with a beginning, right? I mean, those two ideas are really two independent ideas. They become connected in general relativity. But if you didn't have general relativity, and you're just thinking about an era when the universe is hot and dense, why think that there's a beginning? I mean, so, for example, I told you previously that the spacetimes that we use to describe the Big Bang are these Friedmann, Lemaitre, Robertson, Walker spacetimes, these FLRW spacetimes. It turns out that in Newtonian gravitation, there's a very similar set of equations you can write down. In fact, in some cases, they are exactly structurally identical. They have a very different interpretation, because in the Newtonian case, we interpret them as describing not space-time, but the gravitational field. And now you can ask, okay, if we take one of our singular Big Bang models and we come up with the Newtonian equivalent, what happens when we trace the universe backwards? Well, you still end up with that singularity. However, it's a singularity in the gravitational field and not in the structure of space-time. The whole reason why you said that space-time comes to a boundary that we can't get beyond in general relativity was that there was a singularity there. There was a whole surface missing from space-time. So space-time is an actual boundary when we get back there. But in this Newtonian version, well, the field goes to infinity. But so what? I mean, in electromagnetism, the idea that you could have a field that becomes infinite somewhere is a very familiar idea. So in undergraduate electromagnetism, so if anyone takes a class on that topic, they'll know that one of the standard examples that you study is a plane embedded in three-dimensional space, where that plane is it's made of charge. Suppose it's made of negative charge. Well, then the electric field becomes undefined, becomes singular at the location of that plane. But do we think that that's a boundary to space? No, we think that there's locations both above and below that plane, and then you're asked to calculate what the electric field is like in those two locations. So too, if you take this Newtonian model, even though it's singular, because it's not a singularity in space-time, it's a singularity of the gravitational field, you can continue that fine just beyond that singular point. So, it's really this realistic construal of a substance of physical theory that ties together what we can observe with space-time structure, so that you can make indirect conclusions about what the space-time structure actually is. That's what allows for that conclusion. And by denying the link between observations we can make in space-time structure, the neo-Lorentzian has effectively disabled their ability to make any sort of inference that the universe began to exist.
Well, this has been mind-expanding stuff. I wish I had a more robust defense of Craig, because that's the philosophical worldview I imbued in my teenage years. But this is very fascinating. I think you've saved me, if anything, from the excesses of the philosopher of religion's naive views about philosophy of physics. So thank you for that, Dan. I'm sure I'll have you on again to discuss these things more. But thank you for coming on for this. This was really interesting.
Great. I'll look forward to it.